Welcome back. Today we are going to start a new topic and we will be dealing with this topic for quite a few lectures. This is a very important topic as far as heat exchangers are concerned, and basically we are going to look into some typical heat exchanger. Again there are many variations, but we have classified them into or we have assembled them for the sake of understanding in one group, and which I am calling as heat exchangers involving phase change. So, in some heat exchanger we will see that there is a change of phase. So, those kind of heat exchangers we are calling heat exchanger involving phase change or phase change heat exchanger. So, now let us go to the next slide. So, phase change heat exchangers, one of the fluids will change its phase, at least one of the fluid that has to change its phase. In some rare case both the fluids will change phase. So, basically you can understand that we are considering two fluid heat exchanger. Of course, there is no harm having multi fluid heat exchanger. Sometimes again in a very special case one can have multi fluid or multi stream heat exchanger, and then the requirement of its qualification as a phase change heat exchanger is that at least one of the fluid will change its phase. And change of phase could be many, like from solid to liquid, liquid to solid, liquid to vapor, vapor to liquid, but liquid vapor phase change or vapor liquid phase change is the concern. So, either that means the change between liquid to vapor or vice versa is the concern. Basically, the mechanism is either boiling or condensation. In some heat exchanger, evaporation may also be present, like there are falling film evaporator, etc. So, evaporator may also be present in some cases, but mainly we will see that phase change is taking place either by condensation or by boiling. Condensation is also present in case of air being cooled and dehumidified. Very common experience that during summer, particularly in a country like India, when our air conditioner is there and a lot of water drips from the air conditioner, because the hot and humid air comes in the contact of the cooling coil, it gets dehumidified and the air gets dehumidified and the water vapor present in the air condenses. So, then this dehumidifier coil or the cooling and dehumidifier coil of the air conditioner is also taking part in condensation, but those kind of heat exchanger we will not discuss here. There are many direct contact heat exchanger where phase change takes place. So, not very elaborate description of those heat exchanger will be possible with the minimum amount of time we are having. By this time probably you have appreciated that heat exchanger is a vast topic. So, we will try to give some general idea of phase change heat exchanger, and some of the important phase change heat exchangers we will try to deal in a bit details. So, with this let us go to the next slide. Now, here I am showing how the temperature changes in a purely phase change heat exchanger. What is purely phase change heat exchanger? One fluid in the heat exchanger will be changing its phase from the inlet of the heat exchanger till the exit of the heat exchanger. Always if we call this mode of heat transfer or this condition as a two phase condition. So, one of the flowing fluid will always be in two phase condition from the beginning of the heat exchanger till the end of the heat exchanger. So, this is a purely phase change heat exchanger, or let us define it to be a purely phase change heat exchanger. So, as I have told that boiling and condensation are the two mechanisms of phase change which we will consider in our discussion. So, either we are dealing with a condenser or we are dealing with a boiler. So, let us say that we are dealing with a condenser. So, the condenser temperature change is shown here, as it is all through the heat exchanger in the two phase condition. So, it is maintaining that phase change temperature TFC, it is maintaining throughout the length. And then as it is it has to be cooled or heat has to be extracted from here, there is a cooling stream. In case of power plant condenser, let us say the steam is condensing, it is maintaining a constant temperature and water is cooling it. So, water is getting heated up. So, this is the cooling stream which is getting heated up. What is important to see that let us say the first arrangement, the top curve here TFC, that is T phase change, and this is the cooling curve. So, typically this is a parallel flow heat exchanger. Now, if we change the direction of the condensing fluid, so then it becomes some sort of a counter current flow heat exchanger, but the performance will not change. The performance of the heat exchanger will not change. If we keep the heat exchanger design constant, then the inlet and outlet temperatures of the fluid, that will not change. So, it is independent of orientation. This is one thing we have to keep it in mind, that in phase change heat transfer, when there is purely phase change for a particular fluid, it is independent of orientation. So, same thing for a boiler, it has been shown that here the fluid is evaporating throughout the length of the heat exchanger, and probably it is getting its thermal energy needed for latent heat of vaporization from a hot fluid. So, the hot fluid is getting cooled. So, here also the it will not matter whether we are going for a parallel flow or a counter flow. So, LMTD is given by these expressions, and LMTD is independent of orientation. And if we go for effectiveness NTU, all the heat exchanger with phase change will have this relationship. So, very easy to remember. So, this is the relationship between NTU and effectiveness. This is effectiveness and this is NTU, number of transfer unit, and this is the relationship. So, for a simple phase change heat exchanger, this kind of relationship we will get. And I have shown two arrangement, parallel and counter flow. It does not matter which way you are arranging it. Now, this is a cross flow heat exchanger. Let us say our phase change heat exchanger is a cross flow heat exchanger. If you remember, in fin tube heat exchanger, we have taken some example at the end, and we have basically solved a problem of finned tube condenser. So, that was a cross flow condenser. So, here also this is a cross flow heat exchanger. So, for cross flow heat exchanger, let us say this is the condensing fluid, and this is the condensing fluid, it is inside, this will be the temperature distribution, and this will be the temperature distribution at the condensing fluid exit. And as it is in the phase change condition, there will not be any change in the temperature from inlet to outlet, and there will not be any variation of temperature also along the inlet plane or along the exit plane. This is the coolant which is gaining heat. So, when at the inlet it will have uniform temperature, low temperature, at the outlet there will not be any variation of temperature. Variation of temperature at the outlet is characteristic of cross flow heat exchanger, but here we will not get it. So, here we will have this kind of temperature distribution, and so obviously you see that there could be other reasons for selecting the arrangement, whether we will go for parallel flow, counter flow or cross flow. for a phase change heat exchanger, but thermally all of them are equivalent. There could be other mechanical reason, there could be that we have to accommodate more amount of tubes etcetera. So, other reasons, plant related reasons could be there, but thermally they are identical. Cooling fluid temperature is uniform at the outlet. So, this is one very important observation. Now, let us take up a problem. A condenser is required for an organic vapor having a latent heat of 250 kilojoule per kg flowing at 5 kg per second. The vapor is pure and may be assumed to condensate at its saturation temperature of 80 degree Celsius. The condenser is cooled by side cooling water. Specific heat has been given with an inlet temperature of 20 degree Celsius and outlet temperature of 35 degree Celsius. The overall heat transfer coefficient that has been given. Calculate the cooling water flow rate, the value of delta T and the surface area. What is the F value for this case? So, water flow rate we have got. So, from that m dot Cp coolant we can find out, and this is equal to, this is the total heat gained by heat exchange, gained through heat transfer by the cooling water stream. So, this is the heat which is rejected by steam also. So, heat rejected by steam, that will be equal to the steam flow rate and the latent heat, because it is in the two phase condition. So, right hand side everything is known, and from the left hand side it has been told that the water inlet temperature of the water is 20 degree Celsius and outlet temperature is 35 degree Celsius. So, from there we get the mass flow rate of water, that is 19.84 kg per second. So, mass flow of water is known at this point. Next, what we can do? We can calculate the log mean temperature. So, log mean temperature we have calculated. One fluid will be at a constant temperature, that is your 80, and other fluid there will be inlet temperature of 20 and outlet temperature of 35. So, other fluid also we can get the temperature, and from there we can calculate the log mean temperature, which is 52.1 degree Celsius. Now, in this case, as I have already told, that whether we are having cross flow, counter flow, parallel flow, everywhere one fluid is at a constant temperature. So, the flow distribution really does not affect the thermal performance. So, we will get F is equal to 1 for any arrangement. So, that is what has been written. In this case, F is equal to 1. Effectively, the condensing fluid behave as a fluid at infinite specific heat capacity, and the heat exchange is always equivalent to that of a pure counter current flow. Thus, we have got this kind of relationship. This is very important, and you can note this. So, this is one important point, and this is also important to note for a purely phase change heat exchanger. Already I have explained what is purely phase change heat exchanger. So, this is very important to note. Okay. So, please try to correlate the problem which we have done at the end of our discussion on fin tube heat exchanger. That was much more elaborate, because the fin side heat transfer coefficient, pressure drop etcetera we wanted to take care of, but that was also a cross flow heat exchanger. There also we have calculated LMTD. So, please look into that problem, go back to your to my earlier lecture, and please look into that problem. But whatever I have underlined, these points are very important, and this is how we will get the delta T. Now, let us go to the next page. So, surface area we can calculate from here. So, this is our end of the problem. A very simple problem, but it gives us an idea how to calculate the basic calculation of a phase change heat exchanger. Now, you see I have coined some sort of a word or terminology, a purely phase change heat exchanger. Now, most of the practical heat exchangers where phase change of a fluid stream takes place is not like this. So, in phase change heat exchanger we will have change of phase, but before that and after that there could be single phase heating or cooling. So, let us say here we can see condenser with a superheated vapor at the entry. So, let us say this is the condensing fluid which we have to condense, but the fluid is not exactly at the saturated condition when it is entering the heat exchanger. It is the hotter fluid is entering at superheated state. So, if it is entering at a superheated state over here, so then it has to be brought to the saturation condition, and this is single phase cooling for the fluid. Then there will be phase change heat transfer, and then again there could be subcooling, and this is again single phase cooling. And this is how the coolant temperature, coolant is a single phase fluid. So, coolant temperature will continuously increase. I have shown linear, but this curve can be non-linear, this can be non-linear, and this can be non-linear in general. I have shown them linear, drawn them linear, but these curves could be non-linear. So, in most of the practical cases we will get a heat exchanger like this. Let us consider the condenser of a refrigeration unit. So, in a refrigeration unit, after the compressor hot vapor comes out, and that will be in superheated state, and then in the condenser it condenses, either it will be partially condensed or so, but obviously it will enter with a superheated state in the condenser. So, you see that the curve will be something like this and this, either it can go to this range or it can come out of the condenser like this. So, subcooling could be there, subcooling may not be there, but obviously there will be a superheated vapor which is to be cooled first and then it has to be condensed. Next, if we see what is happening in case of a boiler, let us say it is a steam power boiler, steam power plant boiler. So, here subcooled water goes to the boiler, and then there will be vaporization, and then there is superheated liquid, and let us say this is the flue gas. Only thing is that in a power plant boiler this may not be a single heat exchanger. The subcooled liquid and the vaporizer and the superheated liquid or superheated vapor, should be superheated vapor. So, they are not in the same heat exchanger. So, initially there could be some sort of economizer, then there could be boiler drum and the riser tubes in which vaporization will take place, and then there could be a superheater. So, but one can think of some sort of an evaporator where there could be subcooled liquid to superheated vapor coming from the evaporator, and all the three parts will be present. Why I am presenting this kind of pictures, you know, because you have to appreciate one thing, that real phase change heat exchangers are complex in nature. The problem which I have done at the beginning of this class may give a misconception, okay, things are easy because one side the fluid temperature is not changing. One may think that okay, one side the fluid temperature is not changing, so things are little bit easy, but things are not easy because rather the things are more complex, because we have got this kind of abrupt change in the temperature curve. If there is abrupt change in the temperature curve, then what happens? basically we are having 3 heat exchangers. So, we can think that this is one heat exchanger, this is a purely phase change heat exchanger and this is another heat exchanger. So, let me write heat exchanger 1, heat exchanger 2 and we are having heat exchanger 3. So, 3 heat exchanger. So, when I have to do the analysis, I have to do the analysis for 3 heat exchanger. Then there is another thing, let me tell you, probably I will take up this point later on also. Suppose I am a normal 2 fluid heat exchanger and both the fluids are so, let us say this is a counter current 2 fluid heat exchanger and both the fluids are in single phase. So, this side it is temperature and this side it is length. So, here you see the counter current heat exchanger and how I will decide the length of the heat exchanger. One consideration is that the minimum temperature difference which can be allowed for heat transfer to take place, delta T minimum. One can call it terminal temperature difference. So, what is the minimum terminal temperature difference we can allow? That is how I have to, this is one kind of a decision the design engineer has to take. And this takes place at one end of the heat exchanger. That means, this terminal temperature difference is taking place at one end of the heat exchanger. In case of this phase change heat exchanger where there are subcooling and superheating, the minimum temperature takes place here which is called pinch. So, this gives one restriction to the heat exchanger design and this is happening inside the heat exchanger. So, this is very important and we have to maintain a pinch temperature. Probably I will elaborate this as we proceed on and that is how another complexity is added to your phase change heat exchanger. We will elaborate this thing as we will proceed. So, for phase change heat exchanger, we have seen one unique feature that the minimum temperature difference between the two fluids that can take place somewhere in between the heat exchanger, particularly when subcooling or superheating or both are involved in a phase change heat exchanger. So, once again I like to draw your attention to this particular figure. So, I have taken a typical case of a boiler where the flue gas is heating the liquid, so that from the subcooled state the liquid goes to the saturated condition, then vaporization takes place and then we are having superheated vapor. So, superheated liquid it has been written, but it is in the superheated condition. So, it is superheated vapor. So, probably in a boiler we will find this kind of an phenomena, or in a condenser also we can find out the subcooled region, then the phase change region and then superheated region in the reverse order. That means, in case of a condenser it will start from superheated vapor, it will go to the phase change zone and then it will be in the subcooled condition depending on the process requirement. Now, the point which I like to make is that initially let us say we are considering a condenser. So, initially the fluid is at vapor state, its density is low and then it is in the two phase region, the quantity of vapor reduces and the quantity of liquid increases and then it comes out totally in the subcooled region. So, you can imagine that from the beginning of the from the start of the heat exchanger to its end, there is a large change in the density of the fluid or fluid mixture. So, volume flow rate is changing. So, it is a challenge to the designer that how we can accommodate it in a single heat exchanger. Let me elaborate this. Let us go to the next slide. In the next slide, I have shown the schematic diagram and cutaway view of a of an automotive condenser. You know, in cars or automobile, there will be for comfort condition, to ensure comfort condition, there will be a refrigeration system, and in there will be a condenser. Vapor compression refrigeration system. So, there will be a compressor. After the compressor, the compressed vapor, that means which is at superheated state and high pressure, that will enter the condenser. So, in vapor state it will enter, then it will become liquid, and in many cases it will come out of the condenser as subcooled liquid. So, you see, from superheated vapor to subcooled liquid, there is lot of change in density, lot of change in flow rate. How do we take care of it? So, we take care of it very interestingly, we take care of it in this particular heat exchanger by providing different pass. So, you see there are different passes. This is the inlet, this is the first pass, and then this is the second pass, pass 2, and then this is pass 3, and then this is pass 4. Well, the passes are not very uncommon in heat exchanger. In heat exchanger there could be number of passes, and so here also we are having, but what is to be noted, in the first pass where the superheated vapor is flowing, there are 14 tubes. All the tubes are of same dimension. So, 14 tubes means large cross sectional area. As the density is low for vapor, we have to provide large cross sectional area. Then in the second pass, the vapor is now being cooled and it will go to the two phase region. In the second pass, there are 7 tubes. So, drastic reduction in the number of tubes. And in the third pass, there are 6 tubes, and fourth pass, the fluid will be in the subcooled liquid condition, then there will be only 4 tubes. Pass 4, there will be 4 tubes. So, you see, this is one opportunity to see a cutaway view of the heat exchanger. This is a cross flow kind of heat exchanger, which is very common in refrigeration application, refrigeration condenser. So, tube side refrigerant flows, and the tubes are also very unique. You can see the tubes, these are flattened tubes, and in one tube there are 7 passages. So, basically what we are seeing, a cross flow 2 phase heat exchanger using micro tubes, because these passages are of small dimension. This is also a compact heat exchanger, because the area density, area of heat transfer area density per unit volume is very large. And so, this is cross flow, refrigerant is flowing in this direction or in this direction, depending on the which pass it is, and then it is air cooled, or rather the heat transfer is to air. So, air passage is provided by these fins. So, these are the different type of fins, these are the fins, they are attached to the flattened tube. So, on through the fin side air passes. So, this is a very unique heat exchanger, it has got so many speciality. Let me point out all of them one by one. First thing, it is a phase change heat exchanger. Second thing, in this phase change heat exchanger, both all the 3 regions are there, superheated vapor region, then 2 phase region, then the subcooled region. Third, it is a cross flow heat exchanger, it is a compact type heat exchanger. Flattened tubes are used, and in these tubes there are 7 passages in each tube, and the air side is made by fins, and then there are 4 passes, and the number of tube per pass is not uniform to take care of the change in volume. all right. So, one thing I like to mention that we have started our discussion on phase change heat exchanger. Most of the cases I will deal with condenser, that means liquid is condensing. The reverse is the evaporation or boiling of liquid, though we call evaporation, but the exactly reverse of it will be boiling of liquid, and boiling of liquid is needed in many places. But where we are boiling the liquid with the direct application of heat like firing coal or nuclear power or some sort of oil, or in some cases electric heating in small sized unit. So, we call it a boiler. So, where particularly where there is firing we call it a boiler, but we can have boiling in other places also, like in a refrigeration system the refrigerant will boil, but that we call as evaporator. So, what I will do, as mostly I have discussed condenser, evaporators are not very different from them. So, I think one can pick up, but boiler I have not discussed. So, I like to briefly discuss boiler before I end this lecture. So, let us go to the next slide. So, this shows the schematic diagram of a boiler. So, first I have shown supercritical boiler, subcritical boiler, where the pressure of the working fluid is below the critical point, and then I show the supercritical boiler. Here the pressure of the working fluid, that is low at the beginning, but this pressure rises and ultimately this pressure goes above the critical point. So, I have given a name to this slide, boiler as a heat exchanger. So, these two heat exchanger, these are basically heat exchanger, they are slightly different, because in the subcooled condition, particularly if we are away from the critical point, there is a large difference between the density of liquid and vapor, even at a particular saturation pressure or particular saturation condition. So, the same problem occurs here, which I have discussed, that I have to handle subcooled liquid in the economizer, then I have to handle a two phase mixture in the vaporizer portion of the boiler, and then I have to handle superheated vapor in the superheater of the boiler. So, this is true for a subcritical boiler, and generally what happens, boiler is a very big unit. So, there these three, though there is a connection, these three are three different kind of heat exchangers. Grossly if I call them heat exchangers, then these three are three different type of heat exchangers. So, this is your economizer, and in economizer we will find the type of heat exchanger we have studied, it is not much different from that. Then evaporator, which is not this section, but this loop kind of a section. Here of course, we are having a completely different kind of arrangement, which I will explain little bit. This is the main part of the boiler. We do not have much scope to discuss this in this particular course, because boilers are considered as fired heat exchanger, and in our course fired heat exchanger we have excluded. Only a glimpse of it I will discuss, and then after that we will have the saturated vapor, which will be taken to the superheated condition at the corresponding pressure in the superheater. Whereas, in the supercritical boiler, it is sometimes also called once through boiler, because the fluid passes continuously maybe through different sections of the tube, and it enters as subcooled liquid in the economizer and comes out as superheated vapor at the end of the superheater. Whereas, if I see the subcritical boiler, what we will find, there is a loop kind of a thing. Here we will have liquid circulation or liquid and vapor circulation, which is I mean to some extent different from in concept from the other kind of heat exchangers. So, we will look it look at it into little bit details. Let us go to the next slide. So, in this slide schematically a 300 megawatt subcritical power plant is shown. Of course, not the entire power plant, mostly we have concentrated on the boiler side. So, this is the furnace. So, furnace is part and parcel of the boiler. So, you see boiler encompasses many kind of operations, like one is furnace where heat generation will be there, and at the same time the heat exchanger part of it, where from the hot gas or from the hot source of combustion the heat will be transferred to the fluid. So, the furnace here the coal or oil or some suitable fuel will be fired, heat will be generated. So, obviously, the furnace is some sort of a enclosed body, and at the wall of the furnace we can have the tubes, these are vertical tubes, and through this vertical tube liquid will pass, and when it is passing through this vertical tube some amount of vapor will be generated. So, if we go to the previous slide once, what we can find that this is the furnace wall, here heat is given to the flowing water. So, it will get evaporated, but it will not get completely evaporated, partly it will get evaporated and it will come to this circular section which is called steam drum, where the vapor and liquid will get separated. The vapor will go to the superheater, and the liquid, this is called downcomer, through the downcomer it will come. There is a small drum at the bottom, and from this drum again it will go up, which is called riser. So, in a boiler you see there are two very important component, one is a riser and one is a one is a downcomer, and liquid circulation is continuously through this riser to the steam drum and to the downcomer. Here there could be a pump, it could be assisted by pump, or the circulation could be assisted by buoyancy. So, this is completely a different kind of heat exchanger, though it is heat exchanger, but it is a completely different kind of heat exchanger what we find in case of boiler. Let us go back to the next slide. So, here what we can see, so this is the furnace wall. So, this wall are to be kept cool. So, what we do then we provide the water tube through this. So, that is why these are called water wall. So, it absorbs the heat, some amount of steam is generated, it goes to the drum, and then through the downcomer it comes. Now, what is to be noted that in a boiler there are number of heat exchanger and many of them are phase change heat exchanger. So, here of course, some of them are not phase change heat exchanger, but some of them or many of them are phase change heat exchanger. The way I have shown it, this is to make this thing simple, because it will be easy to understand, but actual boiler there will be lot of complexities and pipe layouts are quite complex. So, I will show another slide to give you some sort of an idea. So, what kind of heat exchanger, what we can see here? Here we can see superheated superheater. So, the superheater will be a single phase heat exchanger. This boiler evaporator section, that will be a two phase heat exchanger. Here we can have feed water heater, which is a single phase heat exchanger, but here what we can have feed water heater. So, these are again two phase heat exchanger. So, let us go back to some sort of a boiler. This is how it looks. You can see the vertical lines, these are all tubes, and furnace wall is surrounded by these tubes. So, that the heat absorption is there by these by the water flowing through this tube, and the tube wall is also kept cool. Okay. And here we can see through this nozzle the fuel is injected either in the form of pulverized coal or in the form of oil, and combustion takes place. So, other heat exchangers, if you closely look into this figure, you will find other heat exchanger, reheater, superheater, etc. you will find. So, there is some air preheater also, which is a gas to gas heat exchanger. Quickly let us go to the next slide, which is the last slide of my this one of this lecture. So, here we can see one heat recovery steam generator. So, basically no combustion is there in this case, or maybe some auxiliary combustion is there with the help of burner. So, prior to this there could be some sort of a gas turbine plant, and the exhaust gas of the gas turbine, which is at high temperature, it is coming. So, what I want to show that in boiler there are three operations. The subcooled water is to be brought to the saturated condition. The saturated liquid is to be evaporated, and then the saturated vapor is to be superheated. And though in small kind of heat exchanger we can do it in same heat exchanger, in a boiler there are three elaborate sections. This is the economizer, where the liquid temperature is increased and it comes to the saturated condition. Then this is the boiler, where through circulation we generate steam, evaporator or vaporizer, and after the steam generated we have got the superheater, where the saturated steam temperature is increased. So, this is how we are having a boiler plant. So, this gives in a nutshell some introduction to phase change heat exchanger. We will see more of it, we will solve problem in our next classes, next lectures. Thank you for your attention.